started. This slide is same as last. Tomorrow, don't copy from previous semesters. Grading guideline is the only way we will grade, and make sure you verify your submission, and don't waste any time on 0-point code, okay? So starting, I guess after Thursday, or you can start as early as possible. For kernel 3, we still have the same requirement that every branch of code path, must have at least one DBG statement. And I, posted more stuff in the class Google group. I guess people are still confused about that. So please make sure you do it. Kernel 3, the main thing is that you need to start kernel 3 as soon as possible. Okay, we only have 2 weeks to do it. You really need to get into user space, very fast. Okay, and read the. Make sure you read the spec, and there are hints there how you should start. Please follow the hints. Okay, I guess previous semester, I don't know why people don't follow the hints. The hint says that the first user program that you need to run is hello world. Okay, so that's a really, really good hint. Some people don't do that, and they just go directly to what's mentioned in the Unix documentation, and that's not a good place to start. Okay, start to do things I think the Unix documentation sort of mentioned that, but it doesn't really stress that, so people really didn't really take that hint. Okay, make sure you start with a simple one, and also I guess for our kernel 3, you need to start with only turning on system file system, and don't turn on VM. And there are like 3 functions that you have to implement in handling page frames. So make sure you follow all those suggestions. Don't just try to jump into running user space code right away, because it's going to be very, very difficult. Okay, so make sure you sort of follow the steps. Please also make sure you read the entire kernel 3 FAQ. Even though you don't really understand what's going on, just read through it. So later on, when you get stuck, you say, oh, I think I've seen it in kernel 3 FAQ, and then you will go back and look at it. Okay, and if I have more stuff to add in the kernel 3 FAQ, if people ask questions and there's something that's appropriate, I will add to the kernel 3 FAQ. The midterm has been graded, so I will send the grade to you either today or tomorrow. Please read the grade announcement email very carefully in order to ask for a regrade. And by the way, I'll use the word regrade to mean that even if you just want to see your exam, you don't really want to argue for points or something like that, that's also considered a regrade. And in order for you to do that, you need an appointment from the TA. Okay, so please make sure you follow the instruction in that email in order to get an appointment. All right, the goal today is to finish covering Chapter 7, and there are still quite a few important stuff that we need to talk about. I'm hopeful that we can finish Chapter 7. All right, so last time we talked about the replacement policy, and we talked about that, that in CS 570, you've learned that, the least recently used policy is a good way to go. So the question is, how do you really implement least recently used in the operating system? Okay, and that's the job is going to be of the pageout daemon, and the pageout daemon, it's sort of a parallel, thread that's going inside the kernel. And that thread get woken up once in a while to look at all the pages to see which one it needs to swap out to the disk. Okay, so this is the opposite of lazy evaluation. This is actually doing things very aggressively, and you don't really want to free out. You don't want to free up too many pages because some of the user processes might need them right away. Okay, so it's kind of tricky to figure out exactly what to put to disk and what to keep in memory. Okay, so we're gonna. All right, so over here, right, so the idea over here is that the LIU algorithm, using this example, if you have I don't know if people still use CDs, but if you have CDs, if you have a rack of CDs and it's full, and you bought a new CD, what would you do? Okay, which of the CD you will take off from the rack, and then so to make room for the new CD, okay? Would you do first in, first out, right? The first one that goes onto the CD rack, that's the first one that you remove. Okay, probably, if that's your favorite CD, certainly, you won't do something like that. Last in, first out, okay? Well, I guess over here it says last in, first out is kind of ridiculous as well. Least frequently used, okay? You label your CD and you keep a reference count of how many not a reference count, keep a count of how many CD that was listened to. And the ones that listen to the most, well, that's the one that should be going last. That's reasonable, right? The question is, how do you implement that? So, if you have a bunch of CD, you want to label them with the number of time you listen to it, that's really annoying, okay? What about the least recently used? Okay, if you want to implement a least recently used, right, what you do is that you have a bunch of CDs over here, okay? What you do is that every time that you listen to something, you would, let's say that over here, this is the least recently used. So over here will be the most recently used. Okay, so every time you listen to a CD, you take it out and you shuffle everything back to the beginning of the CD rack, and then when you finish listening to it, you put it back right in the end. So every time you want to use something, you put it in the end, and then pushes everything, to the front. Okay, so in the end, when you need to determine what is the least recently used CD, well, it's the first one right here. Okay, but this algorithm also, it works on a CD rack, but in the operating system, this means that you have to implement a list and you have to keep shuffling the list. Okay, you probably already see some code of shuffling list, right? I mean, this list, you remove something from the circular list and then you put it in the in the beginning or the end. So you can do something like that. Okay, but this is very difficult to do. If you want to figure out which page are actually being used by user processes, right? Because when the user processes are using these pages, the kernel doesn't really get involved, so the kernel can't really do this operation on the fly. Okay, so this operation doesn't work in the kernel. Okay, so what do you have to do? Turns out that this is where we need hardware to help us. Okay, so what happens is that every time when the hardware reference a particular page, as it goes through the address translation in the page table, what it will do is that it will set this reference bit. Right? If it's a write, it will also set the modified bit. And the modified bit is being used to dirty a page so that later on you know whether you need to write back a page to the disk or not. Okay, so what does this reference bit does? Okay, so what you can do is that, so every time when a page is referenced, you can use this bit to, to indicate that that page has been recently used. Okay, so this will take all the pages and then turn them into two categories. One is recently used, the other ones are not recently used. Okay, so instead of using a linked list to sort everything out based on the timestamp or recently used, when they are used exactly, now you only have 2 bits, you only have 1 bit. The bit is 1 to say that this, this page is recently used, and then if this bit equal to 0, that means that this page is not recently used. So the idea over here is that your page out daemon, when it wakes up, it should check every page to see which page is not recently used. If it's not recently used, then you can swap it out to disk. All right, so this is an approximation to the LRU algorithm, and it's a very, very coarse approximation. Okay, but it turns out that this is, reasonable enough to use in the operating system. All right. So what you would do, so in this particular case, I'm gonna, add to this particular page, the previous slide that you saw this picture before. I'm adding the second bit right here. So the first bit is the validity bit, right? This is the V bit, okay, and this is going to be the R bit. Okay, so in the beginning, all the pages are not recently used. Okay, so therefore they're all 0. Okay, as you start running these processes, the processes will start touching some of these pages. Okay, so some of these bits will get turned to 1. Okay, so if this bit gets turned to 1, and this bit gets turned to 1, and this bit gets turned to 1, later on when the page out daemon comes to decide which page to throw out, what it will do is that it will, write this page out to this, write this page out to this, write these guys out to this, etc. All right, and all the pages that are 1, well, those are the ones that are recently used. So, so the idea over here is that if you put them onto, if you swap them out to disk, then as soon as you run those user process again, they might use those pages right away. Okay, so therefore, it's not a good idea to swap them out. But all the pages that are not being used, well, maybe you can swap them out. Okay, so as it turns out, it doesn't really matter whether it's code or stack. You use this single bit to determine whether things are used or not. It's a very effective way. Okay, in the code segment, right? I mentioned that before. Like if you have a Microsoft Word, Microsoft Word is a very, very large program, so the code segment is very large. But most of the code segment is not being used. Okay, so therefore, once you use them, right, you use a certain kind of a filter or some kind of an insert object or something like that. You're not going to use it for a very long time. Okay, so therefore, that segment, then that the pages that are associated with that code, can be swapped out. Okay. Similarly, if you look at the stack, right? If you have a stack, so here's top of the stack, right? So if you have a process that's running or a thread that's running, then you are using mostly the top of the stack. Okay. The bottom of the stack might not be used at all, right? If you're in a recursive procedure call, your stack is going to grow and you're going to shrink like crazy. Right, but but all the other stuff before the recursive procedure call, they tends to be fairly static. Okay, so therefore, again, the top of the stack are the stuff that you can actually swap them out to disk if you need memory. Same thing with the heap. Well, the heap is a little tricky, right? Because the heap is is managed by the first fit memory algorithm. So the objects in the heap that you allocate might tend to be all over the place. Okay, but there might be places in the heap that you don't really reference. So again, those 4 kilobytes pages, can go to disk. All right, so we're going to use this very simple algorithm to approximate LRU, and we're going to use hardware support in order to accomplish this. All right, so how does the page-out daemon work? Right, when do you when do you start? When do you end? Okay, so it turns out that the algorithm that's used by the page-out daemon is called the clock algorithm. So the idea here is that you have 2 clocks, and then they're sort of moving at the same speed. Sort of one guy move this way, one hand move this way, and the other one move this way. Okay, the first hand. So what are these 2 hands in the clock? Right, they are implemented by 2 threads. Okay, one thread set the reference bit to 0. Okay, and the other one check the reference bit. All right, so the idea over here is that you lay out all the pages in sort of a circular way conceptually, or a circular linked list, okay? And then you have one thread. Basically, this one goes around, and this one is the hand in the front. This hand tries to set all the reference bit equal to 0. Okay, so you will set reference bit equal to 0, reference bit equal to 0, reference bit equal to 0, etc. And the second hand, when it comes along, it will check if the reference bit is still 0. Right? If the reference bit is still 0, what does that mean? That means that it's not recently used, right? Okay? If the second hand comes along and the reference has now become 1, that means that between the time this guy set it to 0 and the time this guy tried to check it, that page is referenced. Okay? So therefore, it is recently used. Okay? So you have the second hand lag behind the first hand, maybe by a few hundred milliseconds or something like, maybe by, 1 second or something like that. And then you can make sure that for this user process, what pages are recently used. Or actually, you can actually put all the page frame inside the kernel, organized in this fashion, and check the page, like this. All right, so this is two-handed algorithm. There's also a one-handed version where you don't have the second hand. Okay, then what happens is that the first hand, when it goes to a particular page, it will first check if the reference bit is set. If the reference bit is set, then it's recently used, and then you set it to 0. You sort of reset it to 0. Okay. Otherwise, when you see a page and that page reference is equal to 0, that means that it's not recently used. So you swap that page out. Okay, and then you continue to the next one. All right. So this is the basic algorithm that's being used. The clock algorithm is what's used in the kernel or used by the page-out daemon. Okay. So actually, in Unix we have a non-preemptive system. Okay. So even though we have a page-out daemon, if you have a non-preemptive system, when does this happen? When does the page-out daemon start going to action? Okay. So that's kind of a kind of interesting question. So I think what you need to implement the first function you need to implement in kernel 3 is going to be in this file called pframe.c. So you're implementing 3 functions in page frames. Okay, and one of the functions is called pframeGet. So the idea over here in Unix is that they try to make things simple. So when you try to allocate a page frame and you run out of page frame, well, that is the time to wake up the page-out daemon. Okay, so if you're trying to allocate a page frame and there's no page frame left, so you wake up the page-out daemon. The page-out daemon is going to go through one round of this to free up as much page frame as possible. And if they are dirty, they write them to disk, etc. And then, when you come back to your when you come back to your regular kernel thread, which needs a page frame, well, the second time it comes back, it should see some page frame that are being available. All right, so the page-out daemon is explicitly invoked in the function pframe, I think it's called pframe get. Okay, and that's one of the functions that you have to use. And I guess think the other two you have to implement is pframe pin and pframe unpin. Okay, when you pin a page, or a page frame, that means that that page is not eligible to be swapped out to disk. Okay, if you unpin it, that means that they go back to the list, and now the page out daemon can actually use it, to decide whether to free it or not. All right, so the page out daemon only scan a particular list. So if you want something not eligible to be swapped out by the page out daemon, all you have to do is to remove that page from that list and put it in a different list. All right? Okay, so you'll get to work on that. All right, the allocation, for these pages, where did they come from? So it turns out there are two different kinds of way to implement that. One is called global allocation. You put all the page frame in one pool. Anybody who wants it will get a page out of that pool. So clearly the problem is that if you have a process or you have a thread that's a page hog that use up a lot of pages. For example, if you're running a simulation program that really go out to disk and all it does is keep using more and more memory, that's a memory hog. Okay, so you're going to end up with one thread that's going to use up all the page frames. Okay, so that's not really nice, right? So global allocation, all processes will compete for page frames. Okay, so the problem with this approach is that it's unfair. Okay, so therefore, I guess people come up with the approach of local allocation. Basically, every user process will get a few pages that are private for this user process. Okay, so for example, I just came up with a random number 10. Any user process, if you want to start, give it 10 pages. Okay, and these pages will be reserved for this user process, and these 10 pages will never be given to anybody else. Okay, so why do you want to do that? Okay, so you want to be nice to a user process that's also nice, right? A nice user process is the user process that's not a memory hog. So what it means is that you only use a few pages and then it dies. Okay, so if this user process has dedicated pages, okay, then if it just happened to use less than 10 pages, then this user process, whenever it gets to run, it will continue to run until it dies. Okay, so these user processes will die quickly, so they are very nice to the operating system. So you also want to be nice to them by reserving some pages for them. All right, so that's local allocation. So if you don't do local allocation, here's a silly example that's called thrashing. So the idea of thrashing, so this actually comes, this term was invented in the 1960s when they started inventing the operating system, is that, all right, so I'm going to explain this first and then explain where the term comes from. We're going to have a system that only has two physical pages, right? So clearly this is a silly example. So we have two pages of page frame, frame 1 and frame 2. Okay, and we only have two user processes, process A and process B, and currently process A is using page frame number 1, and process B is using page frame number 2. All right, so if process A only wants to use, this is enough for process A, then process A will be able to continue executing until it dies, and process B will also be able to continue executing if that's all the page frame that it needs. Okay, but what if process A needs a little more? Okay, if process A needs to access a new page, what has to happen? Okay, you trap into the operating system says, I need a new page frame, and there's no new page frame, so it's going to free up this page frame, right? It's going to swap out this one to disk, okay, in order to bring another page in to replace this with process A. All right, does that make sense? Right? I mean, this is the most recently used page because process A is executing, so therefore this one is the candidate to be swapped out. Okay, it's going to swap in a page that's used for A. So what's going on right now, right? So what's going on right now is that process A is going to wait for this page to come from the disk. Okay, so at this time, process A is sleeping on the disk queue. All right, so it's going to call switch to another thread, and now it's going to be thread B, right? Okay, what happens when thread B runs? Thread B runs, thread B is going to get a page fault immediately. Okay, the thread, so this one is going to be in transit, not available to be swapped out because data is coming in from the disk to this one. So thread B is going to cause this page to be swapped out to disk. okay, and try to bring a new page from B onto this one. And when it's waiting for that page to come from the disk, it needs to give up the processor. Okay, and now eventually now there's no threads that are running, right? Because both threads are waiting for the disk. Okay, the disk interrupt happens, free up thread A. Thread A try to execute. Can it execute? No, right? It needs this page in order for it to execute because that's where the machine instructions are. So therefore, page A is going to cause another page fall, and then it's going to cause page, and then it's going to wait for data to come in, and then thread B. So the same thing is going to repeat over and over again. Okay, so this particular phenomenon, in the end, what happens is that if you keep sort of following these steps, none of these processes is going to make any progress. Okay, they are just stuck. Okay, so what happens is that in the good old days, in 1960s, when they discovered that this is one of the problems in the operating system, they will actually hear the disk going crazy, making a terrible sound, and they call that terrible sound made from the disk thrashing, because the operating system is not doing anything, but the disk is going seek back and forth, just looking for the data to be swapped in. Okay, so till today we still call this thing thrashing. All right. So the main problem with this is that you need three pages, but you only have 2 physical pages. Okay, so you don't have enough resources to satisfy the demands of your 2 threads. Okay, so this problem of not having enough resources turns out that thrashing happens in all kinds of systems. It happens not only in the operating system, it happens in database system, it happens in your internet servers, it happens on the internet even. And the usual picture that you will see talking about thrashing is this particular picture. Okay, so the idea over here is that as you're starting to make more demand on your system, so this is a picture of a typical system. When you start making demand, right, in the beginning when you start your system, there's no demand on your system. So the load is equal to 0. Okay, at this point, if you start increasing the load, okay, if you start to say, hey, I have 3 threads I want you to execute, well, guess what? All 3 threads finish. Okay, so the throughput at that point is going to be, every thread that goes in is going to be one that comes out. Okay, so the performance of the system is going to be linear at the beginning when the load is low. Okay, and then as the load getting higher and higher, when you ask the system to run more threads, when you ask the internet to handle more connections, then, it's no longer linear, it's starting to tape off. Okay, and eventually, when you're starting running out of resources, then all you do are useless work, such as swapping and stuff like that. On the internet, it's going to be like packet retransmission inside the internet. All those work are useless work. Okay, so therefore, you get to a place where it no longer levels off; it actually falls off the cliff. Okay, so this is the region where thrashing happens. Okay, and it happens on all the systems. So what do you have to do in order for you to avoid getting into that system? Okay, so if you want to, if you learn, control theory, right? The control theory says, well, all you have to do is control it. I can actually draw something called a load line, and then find an operational point, and then you stay right there, and you'll be safe. Okay, so you can actually try to make sure that you stay around this particular curve, where this, this part of the curve, so your system is relatively efficient. Okay, so that's good in theory, but exactly how do you implement it? All right, so the idea over here is that the way that we can implement it, so this is like study in the 70s, to try to solve this problem, is to use the idea of a working set. Okay, so the idea of the working set, and again, I say use the idea of the working set, because as it turns out, working set is very, very difficult to implement, so we can again try to approximate the idea of working set. Okay, the idea of working set is that a set of pages that are being used by a program, where's the definition? All right. Oh, over here is the working set, right? The working set is a set of pages that are used by a program. Okay, so if you look at a program, right, this is time. Okay, at time, you can look at all the pages that they are being used by this, by this particular thread. And over here, I'm just going to count the number of pages that are being used. Okay, so when a program runs at different phase of your program, you actually use different number of pages. Okay, so over time, maybe in the beginning you use this many pages, later on you use this many pages, and then later on you use this many pages, and then you use this many pages and stuff like that. Okay, so a long-running user process, the number of pages that you use actually changes over time, and the actual pages is the working set. Okay, so if you know that the program behaves like this, what would you do? Okay, if you want to prevent thrashing, right? So what you want to do is that you want to say, hey, if the program is in this phase, then I want to make sure that it has this many pages. Okay, does this program needs more than this many pages at this time? No, right? If you allocate more, it's all the waste. So if I can know exactly what is the working set of a thread, I can allocate, or the kernel can allocate just the correct number of pages for this process, and then this process will, and if I can do that for every thread inside the operating system, then is it possible for me to get into thrashing? Okay, if all the threads got all the pages that they need, then I can never get into thrashing, right? Because if you add up all the number of pages that you can use, it's never going to be larger than the number of pages that's needed. Okay, any thread that cannot get this many pages, right? So over here, if I'm in this page, in this phase, okay, and this one needs that many pages, and I cannot allocate that many pages to this user process, what I'm going to do is I'm going to take the entire process and swap it out to disk. All right. If I do that, then this thread will not compete for the physical pages. Okay. So therefore, in that case, I only keep what's running if they can satisfy their memory requirement. Okay. So the working set idea is that if the operating system is so smart that can figure out how many pages does each process need, then it can allocate just the right amount of pages, and then all the other ones that are memory hogs, put them to disk. Okay, and then all your thread will continue running until they get into the next phase, right? Once they get into the next phase, then you can adjust your working set, and then now you free up some pages over here. You can start bringing some more threads from the disk to have them run, or in this case maybe processes. All right. So how do you know for a thread how many pages it needs? What is the working set? Well, it turns out that's very, very difficult to figure out, right? So that's why, instead of trying to figure out exactly how many pages are being used by a thread, I guess you can have the thread to declare, so at this point, I need 10 pages. At this time, I need 20 pages. But that's really put a lot of burden on the programmers, to write this code, for the operating system. Okay, so therefore, the operating system decided to do an approximation of this one, and the basic approximation is just to use, local allocation, right? If you are a small process, then I'm going to give you, I don't know, 10 pages, 50 pages, 100 pages, whatever the number is, I'm going to give you that pages so that you don't share that with anybody else. And if that's all you need, then you guarantee to run, you guarantee that you are not going to get sort of, if you continue to use that, you're not going to get swapped out, and then you get to finish execution, and then you will free up all your pages. All right, so that's the idea. Okay, all right, the next part of the virtual memory, we're going to see some of the systems. We're going to see Linux, and then we're going to sort of briefly look at Windows, or just look at it a little bit. Okay, Linux virtual memory layout. Okay, so I guess, I sort of talked about this before, right? The kernel address space is actually take up the top part of the user address space. Okay, so the user address space doesn't go from 0000 all the way to 0xFFFF, right? Okay, in reality, the top of the user space is 0xBFFF, BFFFF. Okay, so the kernel, actually, the starting point of the kernel is 0xC0000000. Okay, so this is 1 gigabyte, and this is 3 gigabyte. All right, so this means that all the user processes, the usable memory is from here to here, and this is, sort of the starting point that the user can use, and the stack grows this way, and the heap grows that way, etc. Okay, and this is Linux. So you're going to use the memory map, right? So again, this is the map. Okay, that map the entire 4 gigabytes of address, 32-bit address space to physical memory. Okay, and physical memory could be, from 1 gigabyte to, whatever the number is. Right? Okay, so who is managing, the physical memory? Okay, so over here, here's a slide that says, well, for user processes, well, the user only do memory allocation in virtual space. Okay, so when the user call malloc and stuff like that, they're allocating stuff in virtual memory, and the operating system also does the same thing. most of the stuff is done using virtual allocation. Okay, and this is done, when you need to fork a process, all the kernel's data structure, if you want to allocate new stuff, when you call the slab allocator, well, their allocation is done in virtual memory space. Okay, there's no physical memory. Okay, so the real allocation that the kernel do when the kernel try to keep track of physical memory, okay, what it does is that during time of page fault, okay, when you have page fault, right, you trap it into the kernel need to find a page frame or find a physical page where that will allocate it to this process for it to be used. Okay, so only at that time it does physical allocation, right? So over here it says real allocation or physical memory allocation. It's only done during the time of page fault. Okay, all the other time, it's all virtual allocation. Okay, and some kernel data structures, some special kernel data structure, are done using physical allocation. For example, the page table, the page table has to be sitting in physical memory, and we said that the page table, the base of the page table, which is the page align address, that one is kept in the CPU in the CR3 register for Windows. For Intel. Okay, so those allocation are done using physical allocation. Okay, so this is, and I guess we also mentioned that in Intel, they use multi-level page allocation, right? And the page directory table is fits into one page, and the individual page table also fit into individual pages. Okay, so when you try to do management of the page table, you are also doing physical allocation. Okay, and that's pretty much all the physical allocation that you will do inside the operating system kernel. All right, so what do you do when you have small amount of memory? Okay, so here's an example where we only have 1 gigabyte of physical memory. Okay, and any user process will have 4 gigabytes of virtual address space. Okay, so how does that work, right? And over here, if you think about this, the kernel is 1 gigabyte, right? So the kernel just uses up the entire physical memory, and then we're done. The user cannot use anything. All right, so that doesn't sound right, right? So something is going on. Of course, what's really happened is that the real memory, you divide into pages, right? Some pages are used by the user, and some pages are used by the kernel. Okay, so so these pages that are used by the user, can the kernel get to those pages? Right? I mean, the kernel has 1 gigabyte of address space, right? So the kernel actually has a very straightforward mapping from the virtual address space to the physical address space by doing a one-to-one map for every memory location over here. They can map it to physical memory. So the kernel can actually, if you only have 1 gigabyte of physical memory, well, the kernel can actually access every memory location over here. Even some of them belong to the user. Okay, so that creates sort of kind of a strange, picture, right? So over here, so if you look at this picture, we have user process number 1 and user process number 2, and these are specific to user process number 1, and these are specific to user process number 2. And when they trap into the kernel all starts at exactly the same address. Okay, so therefore the kernel, the address space is shared. Well, there's only one kernel, right? So they all share the same address space. So when you go into the kernel basically uses the same memory map. Okay, whether you come from the user process number 1 or process number 2, when you go into the kernel, all you need to do is to map the top 1 gigabyte of the address space to physical memory, and you can access any memory location. All right, so when you switch from one process to another, right, the OS code and the data, they stay exactly where they are in virtual address space. Okay, so kernel is executing in virtual address mode, right? It only generates virtual memory references. It do all the allocation using virtual addresses. Well, and it doesn't really matter what it's doing for one user process or another process. It's all the same. It's all the same address space for the kernel. Okay, so if you have only 1 gigabyte of physical memory, the OS can read and write every piece of user memory easily and directly. Well, directly meaning still going through the memory map. Okay, so over here I wrote the word map over here. Actually, there are 2 maps going on here, right? One is the user memory map, and then the other one is the kernel memory map. When you switch from the user process to the kernel process, well, you have to use a different memory map. Okay, this memory map is sort of straightforward. Map everything over here to physical memory. And then this one tends to be kind of sparse. Okay, so in this picture, right, the text region over here is mapped to this part of physical memory, and for this user process, its text is done over here. Okay, does the kernel need access to these memory locations? Of course they do, right? Because when you trap into the operating system is going to cause the disk to transfer data from the disk into memory. It's going to the same piece of memory. Okay, so the kernel needs to be able to write this piece of memory, using the disk controller to do all the data transfer and stuff like that, or the disk driver to do all the data transfer. Okay, so over here, all right. So So these code and data, they can be swapped in and out. Okay, it depends on how you set up the map, right? So there's a map over here, and over here there's a map, and this one uses the same map when you're executing the kernel. Right, so this picture, there's 3 maps, one for the kernel, and one for user process number 1, and one for user process number 2. All right, so the picture in the kernel is actually fairly, convoluted because they all share the same physical memory. Okay, these user processes, they don't really share any memory. Okay, because we want to make sure that they're isolated, right? Except when you're doing copy on write, where you're sharing data, you're sharing code segment and stuff like that. But otherwise, they're really not allowed to write into each other's memory locations. Okay, but the kernel can actually write to any one of the user memory location because the kernel is all powerful, right? It can go mess around with the user, memory space if they want to. Okay, so this brings to this next page. So over here, for the kernel 3, one of the things I sort of want you to do, I'm saying homework, you don't have to turn it in, is to read this particular code to see how Unix set up the memory map. Okay, in the beginning, there's no user processes, only the kernel. The kernel address space is 1 gigabyte big, right? It goes from 0xC00000 all the way to 0xFFFFFFF. By reading this code, PT init, page table initialization, you're going to see how the kernel actually set up the first page table. Okay, and this code was actually executed before Bootstrap. So before your kernel 1 is actually starting to run, this code has been executed already. Okay, so it's going to be difficult to set a breakpoint over there. But you should read the code and try to understand what's going on. How does the page table getting initialized? Okay, so this one is in kernel mm. There's a file called pagetable.c that implements all the functionality of the page table. Okay, so it shows that the kernel text data and BSS starts at the virtual address 0xC00000. Okay, so actually right here, this is the kernel text. Kernel text is right here. Okay, and then the kernel data segment, and from that point on, it's tons of stacks, all kinds of crazy stuff. And turns out that right after the data segment, right after data segment is the heap segment. How does the kernel allocate data from the heap? I mean, does it use a memory allocator? Actually, as it turns out, the kernel doesn't really care. The kernel just uses a regular, when it needs pages in physical memory or in virtual memory, they can just use its own buddy system to do the page allocation. Okay, so what happened is that the first memory allocation that the kernel does is right above the data segment, okay, where the heap is. The first thing that is going to allocate is the page directory table for the kernel. Okay, as it turns out that this one is actually, it's 2 pages big, it's 8 kilobytes long, okay, and I think that's because the way Intel hardware is specified, that's what you need. So remember, the page table is something that the hardware understands, okay, so when you try to construct the page table, you have to, I guess in our class, you don't really have to look at the Intel hardware spec. You can just look at the existing kernel code, try to sort of figure out what do you have to do. Okay, but you sort of need to understand what kind of fields are in them, what are important to set, and look at reading this code should help you to set all the bits in the kernel page table. All right, and then for the user page table, you have to set up something very, very similar. All right, so the first 2 pages in the heap is going to be the page directory table for the kernel paging scheme, and then comes the kernel going to use a bunch of pages, and then the next few pages are the kernel page table, and each one of them is 4 kilobytes long. All right, so read this code to find out exactly how this is done. Okay, And you need to understand how memory map is set up in the kernel. And you also need to understand that, once you start doing this, after that, the kernel, basically just use the virtual addresses for pretty much everything. All right, except when you try to allocate a physical page to handle page faults. Okay, and inside the kernel, when you're running the kernel, you shouldn't have any page faults. Okay, only the user processes are allowed to have page faults. Finally, here's a sort of an interesting point. You understand that every physical address can have two virtual addresses. Okay, if this is physical memory, look at this memory location right here, right? Okay, how many virtual addresses does it have? Okay, so this is a page, inside the physical memory, right? So you got to have at least two virtual addresses. One is for the user application. This one is going to have a virtual address to access this particular page. And also the kernel needs to muck around with this page. So therefore the kernel also have a virtual address for this particular page. All right, so if you want to, when you find a physical page and say, what is the virtual address for this page? You should say, well, for whom? Are you trying to look up the virtual address for the kernel, or are you actually trying to look up the virtual address for the user process? Okay, because the kernel cannot use the virtual address for the user process, even though the kernel knows what's going to be the virtual address for the user process, right? Because the kernel knows everything. It knows how to go through the kernel data structure to find out how the memory map over here is set up, so they will know that, for this page, what is the virtual address that's being used by the user process, and then it can go ahead and over here and try to, change that particular memory location because it has its own virtual address to mess around with the data over there. Okay, so this is also a very important concept, and maybe co-segment is kind of a silly thing to look at, but if you think about when you make a system call, okay, when you make a system call, how do you get the return value from the kernel? Right, so for example, if you want to call read, the read system call, you're going to pass a memory buffer to the kernel. So how do you pass a memory buffer to the kernel? Well, you have a virtual address from the user space, right? The virtual address could be somewhere in the stack, could be somewhere in the heap, could be somewhere in the global data area. So it's a virtual address of the user process. You pass that information to the kernel is going to look at it and says, oh, it's a virtual address of this user process. I'm going to see where I have to write to in the kernel using the kernel virtual address to write to that memory location. All right, so that's where some of the confusion comes from. But when you start to get confused, look from physical address map to virtual address. You have to remember that every physical address can have potentially two virtual addresses, okay, or maybe more. If you're sharing multiple files or something like that among many user processes, I guess Unix don't have to worry about that because Unix is very simple. All right, so things get ugly, when you have to deal with that. All right, so when you deal with user processes, you got to worry about these complications. All right, so we're still talking about Linux. So for Linux, what if you have a lot of memory, right? These days, your laptop has 8 gigabytes. Okay, the user, the address space, may only be 4 gigabytes long. How do you access 8 gigabytes? Well, some of them are using hardware support. Okay, so let's say that you have more than 1 gigabyte. Okay, so the way that you use this upper part of the memory is to use something called the kernel map. Okay, the kernel map is a special map that's set up for the kernel so that the kernel code actually is only going to take up 15/16 of the kernel address space, while the top 1/16 of the kernel map, the top 1/16 of the kernel address space, they can be remapped to any part of the physical memory. Okay, so we're going to use one map for mapping the bottom part into the bottom. In this case, this is 896 megabytes, 1/16 of 1 gigabyte. Sorry, 15/16 of 1 gigabyte. Okay, so this one directly mapped to the bottom part of the real memory. Okay, the top part you can change the kernel map so that it can map to any part in the physical memory. Okay, so if you have a user process, this user process is actually using this part of the memory. Okay, and now the kernel needs to go change some value over there. It will set up the kernel map so that it will point to this region so that it can change the values over there. And if this region is bigger than this one, you have to keep changing the kernel map so that you can modify the right part of the physical memory. Okay, so if you want to change the location over here, you set up the kernel map to point right here. And later on, if you want to change this location over here, you have to change the kernel map so that it points to somewhere higher over here, and then you can modify the location there. Okay, so this is how the kernel can actually, access any part of the physical memory. All right, again, using memory map techniques. All right. Well, as it turns out that in Linux, they actually divide memory into 3 different zones because there needs to be something special for the devices. Okay, most of the devices out there, they don't really use a 32-bit physical address. Okay, so again, where are the devices, right? You have the bus. Okay, here's CPU, here's memory, and then here's devices. Okay, there are many, many devices. Okay, the physical, this one might be 1 GB. Okay, but these devices, some of them, the address that get that get outputted from the device, they are usually at most 24 bits. Okay, some of them are capable of doing 32 bits. Okay, but there are some devices that can only capable of doing DMA using 24 bits. Okay, so if you use only 24 bits, then they can only go to a certain part of memory. So therefore, those memory are reserved sort of for the devices. Okay, and this address range is called DMA zone. All right, so the memory location go from 0000 to 00FFFF. Sorry, FFFFF. Okay, so the top, I guess the top 8 bits are all 0. That's called a DMA zone. Okay, so those memory locations are reserved for data to be transferred between devices and the kernel, and so therefore those addresses you're not supposed to use. Okay, and then comes what's called a normal zone. The normal zone goes from the end of the DMA zone to 2 to the 30 minus 2 to the 27. Okay, so that's exactly depicted in the previous picture. Sorry, that goes all the way up here to the 896 megabytes into the kernel. Okay, so the bottom part is reserved. Okay, so this is all the way to 0x00FFFF. Sorry, FF, and this is the DMA zone. Okay, so the user actually is not, the user processes are actually not allowed to do this. So therefore, referencing memory locations 0 is not allowed. All right, because you're in the DMA zone, so therefore that's reserved. Okay, so we don't really start at 4096. We actually start at 0x01000000. All right, and then on top over here, go all the way up here. This is called the normal zone. Okay, so where the kernel, data structures lives, and maybe some of the user data structure will live right there. Okay, the normal zone goes from 2 to the 24 all the way to 2 to the 30 minus 2 to the 7. And the OS data structure, they must sit inside this normal zone. Okay? If the OS doesn't take up that much room, then yeah, you can also have user pages sitting over here. Okay? And then anything above that, okay, and clearly, so anything above that is called a high memory zone, starting from anything greater than 2 to the 30 minus 2 to the 27. From that point on, this is strictly used for user pages. Okay, so the kernel basically can really not really use up more than 15/16 of the 1 gigabyte that are used for the kernel. And how big is the kernel anyways? I mean, it's not that big, right? Okay, if you look at the Unix code, the kernel is not that, So this is plenty of space in the normal zone for the kernel to run. All right. Okay, so the way that the pageout daemon works, okay, is that they use this LRU mechanism. For Linux, they manage all these 3 zones differently. Okay, every one of these zones they have their own own memory allocation to work with. Okay, if you have a bunch of pages, so this is between 0 to 2 to the 24. Okay, all these pages, they form a pool of pages over here, okay? And all the pages in the normal zone form a pool of pages over here, and all the pages in the high-man zone, they pull them together. Okay, so the idea over here is that if pages are actively being used, then they sort of get on this list called the active page list. Okay, otherwise, well, they are free. Okay, but if the pages that are being written out, you sort of have to pin these pages down or lock these pages down. So for those, during the time when you try to write a page out, you got to make those pages inactive. Okay, and then eventually when you write those pages out onto disk, then they can go back into the free page list. All right, so the way that the pages get cycled, or the life cycles of a particular page, is that a particular page can be either be free, or be on the active page list, or be on the inactive page list. Okay, a page started out in the free list. Okay, and whenever you do memory allocation, right, then they go onto the active list, they become active. Okay, and then when the pageout daemon runs, the pageout daemon decides that this particular page is not recently used. At that point, it will move into the inactive pages so that it can be returned back into the free page list. All right, so the page sort of goes through this particular cycle. Okay, if the pageout daemon decides that that particular page is recently used, then it stays on the active page list. All right, and these three different zones are managed, sort of differently. Okay, I guess over here, here's the words for it, right? If a page is in the free list, that means that it's not being used by any user process, and we're going to use the buddy system to maintain it. I think in the Unix code, page.c, okay, you can read the code to see how the buddy system works. The code is pretty complicated, so I suggest you don't spend too much time on it. And also, it's very confusing. All right, you just trust that it actually works. All right, so in this case, since the buddy system, is used to maintain, then the contiguous memory in real addresses also they have contiguous addresses in virtual address space. Okay, and this virtual address space means it's the kernel's virtual address space, because the kernel is going to use the buddy system to allocate pages to be given to users. And when those pages are given to the users, those pages now have two virtual addresses. One for the kernel to modify stuff, to write stuff into, and the other one is for the user to use. All right? The pages that are inactive, if they are picked out by the clock algorithm as not recently used. Okay? And the page belongs to the active list if it's picked out by the clock algorithm as recently used. All right, so that's sort of the simple definition of these bits. The simple address user space looks like this, okay, and the address space is represented using something like this. Okay, when you're starting to add memory map file or stack and stuff like that, the address space is starting to get more complicated. So this list can start growing to be very, very large if you start running a lot of threads and use a lot of memory map file. Okay, so again, if it's a linear list doesn't scale very well. So in reality, in Linux, what it will do is that it will use a tree data structure to maintain the address space. All right? Okay, so a summary page for the Linux page management. They use a two-handed clock algorithm. Okay, and they use separate zones. They use 3 different zones, and each one of them has their own managed page list. Okay, and then so the idea over here is that those pages are shared among all the user processes, but they're separate into zones. So essentially we're doing global allocation in Linux. Okay, Windows does something different. All right, and this I sort of mentioned already. Right, the pageout daemon. What the pageout daemon does is to scan. So where does the pageout daemon scan? Right, the pageout daemon, when it's get activated, what it will do is you need to scan all the active pages in order to figure out which page to move into the inactive list. And if the bit is dirty, then they get written back to disk. If the bit is not dirty, then this page basically can be moved directly back into the free page list. Okay, so over here again, I shouldn't say the free page list because the pages are using the buddy system, and things are really not arranged in a list data structure. It's arranged in this funny tree data structure that we briefly mentioned before. All right. All right, so some important Linux virtual machine data structure that for every process, the process control block contains the address space representation. Okay, so the address space representation in Linux, this is basically called, it is the memory map. Okay, how to map the user address space to physical address, well, that is the memory map, so that is the address space representation. Okay, so the address space is the memory map, right? It maps the virtual memory segment to physical memory segment. It also keeps track of where the backing stores are. Right? Remember I said, every memory pages, if you need to swap out the entire process, you need to have a place to go, and that place to go is called the backing store. Okay? And some pages don't need a well, some pages, like the text segments and the data segment, for a user process, they don't really need a backing store because you know where to get them from. Okay? The other kind of memory objects that you sort of need to be explicitly allocate backing stores for them. Right? And we're going to talk about that a little later. All right, and then in Linux, you need to allocate page tables for these user processes. Globally, you maintain this free and an inactive page list, and use things like the buddy system to manage the free list, the free data. All right, so again, all right, what happens when a page fault occurs? Right, the good old stuff we talked many times. Page fault came from the hardware because validity bit equal to 0. Now you trap into the kernel, and now we know that there are these data structures you have to go through. The kernel needs to grab a free page frame if it's available, okay? And then what it needs to do, and this is what sort of the hard part. Again, Unix is not Linux, but the idea is very similar. You need to look at the memory map, okay? Look at the address space to see which process caused the page fault, and start walking down its address space to figure out what you have to do, okay? And then copy the page from disk into the free page frame, and then you adjust the page table to point to this page frame, and then you restart. You're going back to the user space by return back from the trap, and then the user will reissue that memory reference, and this time it should go without a page fault, right? Unless you're in a strange thrashing situation, otherwise you shouldn't get a page fault. All right. So this gets a little more complicated, because the page frame may be shared by multiple user processes. Okay, so even though this is the very simple step, when you try to look up these things, things can get pretty messy. Okay. All right. What happens when the pageout daemon wants to free up a modified page? Okay, you pick out a page to be that's not recently used, but this page is dirty, so you have to write to disk, right? So this is kind of like a concurrent activity in real Unix or Linux. In this case, what you need to do, right, you need to find out, okay, from which process or the address space the page frame belongs to, okay? Because, so in this case, you're sort of doing a reverse lookup, right? If you're the pageout daemon, you're going through this data structure, trying to find out which page frame that you need to free up. Okay, as you go through that data structure, you need to make sure that the page frame has a way for you to point back to see which user process it belongs to. Okay, so therefore, part of the job is to find out which process and address space that the page frame come from, because that particular location has important information to tell you where the backing store is. Okay, so you have to do a reverse lookup from physical, page frame, going back to, the address space to try to find out where does that, where should it go. Look at the memory map and find the corresponding backing store, and then at that point, you can issue a command to write that page out to disk. Okay, at the same time, you want to sort of pin that page up so that, no pageout daemon is going to come, maybe the other hand is not going to come and mess it up. By doing something with it, all right? And when this is all done, you unmap the page from the memory map for that user process because this page is no longer available, and then you want to free up the page frame, all right? Send it back to the buddy list, and the buddy list can start allocating, reallocate that page again. All right, and again, things get more complicated because page frame can be shared by multiple user processes. Okay, so that's Linux. Windows, and again, Windows is more complicated. So to start the complication, the Unix actually offer two different ways for the kernel for the kernel address space to be used. And this depends on what kind of kernel you have, right? Windows actually has so many different versions of Windows. Some are for enterprises, some are for the cloud, some are for personal computer and things like that. So, and Windows has a very, very large user base, and they have to satisfy every kind of users. Okay, so they actually provide two different ways. One is just like Linux, right? You have 1 GB for the kernel and 3 GB for the user. But you can also, when you configure the operating system, you can choose the other approach, the other way to have a larger kernel. Okay, maybe because you have a lot of device driver, and stuff like that. So you would choose something like this, where you have 2 GB for the kernel and only 2 GB for the user space. All right, and these things are sort of done at configuration time for the kernel. Here's a summary, and again, we're not going to go too much into Windows, so we just have sort of a summary page talking about, what are the, what is the window paging strategy. Every process is guaranteed a working, sort of a working set. So they don't really try to implement the actual working set. They try to do local allocation to reserve memory pages for every user process. Okay, so this way, small, a process that has small memory requirement will always execute, until completion. Okay, if you have a process that needs additional pages, then you need to compete for that in a global pool. Okay. The Windows use a one-handed clock algorithm instead of a two-handed clock algorithm. And then they also have a swapper thread in the kernel, try to swap out an entire user process. Okay, what it will do is that it will look for user processes that has been idling for 15 seconds, and they will swap the entire process out. Okay, first it tries to stack, and then the other memory, and this is very different from Linux. Okay, so I don't know if you notice this from Windows. Let's say that you have a web browser that has a lot of tabs open, and then you don't use it for a while, and later on you try to switch to it, it will take a very, very long time for the kernel to swap that thing back. Okay, if that thing been sitting around idling for 15 seconds, then it's going to take a long time to bring it back. Some of the kernel pages the kernel memory is page. I think Linux also does the same thing. Page fault is possible in the kernel. Okay, just like Linux. Things that are not supposed to be page out, you got to make sure that you lock them down. Right? So clearly the code for the page out daemon, you should make sure that those code are never be eligible to be swapped out. All right? Okay, so the next thing we're going to talk about is this very important topic. It's going to create a lot of complication in the kernel, in kernel 3. That's called copy on write. And we got to make sure that that works with fork. By the way, is fork very important? In warm-up number 1, warm-up number 2, you don't do any fork, right? We do multi-threaded program. Why do we need fork? Right? Because the first time you run any user processes, you are doing forks, right? Okay, when you log in, remote login to Nunkey, right? The rlogin fork off your login shell. Your login shell, every time you're typing any command into your login shell, you are doing forking. Okay, so forking is something very important, and we have to take care of it. All right, so it's kind of funny that in this class, right, the first system call we introduced is fork, and now, again, we try to cover fork. And turns out in the kernel assignment, the fork is probably the last API you have to implement because it's really complicated. All right, and then to make things even worse, we got to handle copy on write together with fork, because we have to handle fork, and then because we're doing demand paging and we want to be very efficient in the use of memory, we have to do copy on write. Okay, copy on write makes make fork really fast, right? Because we just copy the entire page table from one user process to another. Okay, and then we have to use copy on write so that when you try to write to pages for the first time, then that's when you allocate new pages. All right. Anyways, we're going to look at what is the issue to do these two things. So first, we're going to look at fork a little bit, right? Fork. The problem with fork is that the abstraction is that when you fork of a child process, you get a copy of the entire address space. Okay, and copying the entire address space is too slow. Okay, so eventually we need to get to copy on write. So before copy on write, people actually have a different solution. This solution is called vfork. Okay, when you do vfork, so the idea over here is that when the parent process, here's the parent process. Okay, when it creates a child process, it actually let the child process borrow its address space. Okay, so the idea over here is that when you call fork, you're inside the kernel will suspend the parent process, will pass the address space to the child. Say, child, go ahead and use it. Okay, because, what is the child going to do? Well, most of the time, the child is just going to do exec, right? Okay, so therefore, as soon as the child called exec, then the address space is returned back to the parent, and now the parent is allowed to execute in parallel again. Okay, what if the child process doesn't do exec? Well, then it's an issue, right? So basically, they put the burden on the programmer. So the programmer is writing code for both the parent process and the child process. So the programmer needs to know when to make a call to fork and when to make a call to vfork. Okay? If the purpose of creating a child process is to do exec L right away, then you call vfork and temporarily loan your address space to the child process. As soon as the child process call exec L, well, you're back into the kernel, and the kernel can return the address space back to the parent process. Okay, so this way, you don't have to copy anything. Okay, so what's wrong with this approach? Well, because it's on the burden of the user, of the programmer, and the programmer has to decide what has to be done. Okay, if right before you try to create a child process, you have to actually modify the address space, then you can't really use vfork, right? Because when you use vfork, you borrow the parent's address space, and if you go and modify some global variable, the parent process is going to be very surprised when it gets the address space back. Okay, so this required the application programmer to understand all these things that's going on, and so even though this one has very, very good performance behavior, but the complication is what killed this particular scheme. Okay, so these days what we do is that we do copy on write. Okay, so what we do is that when the parent process, okay, fork off a child process, right? We make a copy of the address space, okay? But we don't really copy the data in the address space. We just copy the data structure. Okay, we also copy the page table, right? If this is the page table, we make an exact copy of the page table, okay? And then from this point on, we're going to do copy on write. Okay, what does it mean to do copy on write? Right? Anything that's supposed to be writable over here, if you have something that's read-write over here, okay, when you make a copy, then this one is going to become read-only. Okay, so this way, right, they can actually share the same physical page, but when this guy tries to write to it for the first time, you're going to get a copy of the page and you write to the copy. Okay, so given your understanding of copy on write, so we can see that this, this works reasonably well. Right, as it turns out that because you need a fork, that makes things a little complicated. All right. We talk about lazy evaluation, right? So, here's an example of copy on write, right? Here is the parent page table, okay? And here is the child page table, okay? So when you go copy on write, before that, every pages that they share, these are data pages, they're all read-only. Okay, so in that case, if anybody tried to write to it, then you're going to trap into the kernel, and the kernel is going to perform copy on write. All right, so that's how the basic, the first step of copy on write is to protect all the pages, make sure that they're only read-only access. Okay, and then what happens is that when you try to write to it for the first time, then you're going to cause a page fault. Right? So if the parent process says data equal to 17, and the data is this page right here, okay, then that means that it's going to access this particular page, and this write data equal to 17 is a write memory location, so it's going to cause a write to this page, and this page is read only, so therefore you're going to trap into the kernel. Okay, the kernel is going to say, well, who summoned me? Goes down to the data structure, find out it's this process that's accessing this memory location, and that's why you have a page fault. Okay, and also at this point, the kernel actually knows that it's set up for copy on write. Okay, we mentioned before that there is a flag called the private or the share flag. So if this particular page is private, okay, then the kernel will perform copy on write. Okay, but if you look at this picture, where's private? Right, there's no private or share. Okay, so it turns out that as you walk down the kernel data structure in in the memory map, okay, inside the memory map, that's where the information is, whether this particular page is shared or private. Okay, so therefore it's very important for the kernel to walk down this, this path in order to determine whether it needs to perform copy or write or not. Okay, so if it's read-only and the memory map says that it's private, then you know, and you try to do a write operation, all these three conditions has to be true, and then you know that you have to perform copy on write. Okay, so at this point, to do a copy on write, you make a copy, right? You make a copy of this thing into this. Oh, actually, I'm a little ahead of this time. So at this point, when you make a copy, this data is equal to 0. Okay, you fix the page table so that this guy will point right here, and then you change this entry to rewrite. Okay, and then you return back to the user process to have it repeat that operation. In this case, it will be, again, it will repeat data equals 17 again. Right, so therefore, you try to write to this location with a value of 17. In this case, as it goes through the page table, it's going to allow it to go through because it's rewrite. Okay, and then the memory location is going to write to is going to be writing to the copy and not the original piece. Right, so therefore, this guy will change from 0 to 17. All right, so this all works, right? If the child process needs to write to, say, data equal to 5, well, exactly the same thing happened. You trap into the kernel get a page, you copy, you copy this thing into here, change the pointer to point to this one, restart and change this one to rewrite, restart the operation, and then this one is going to be equal to 5. Okay, and then who's using this guy? Maybe nobody, all right? Maybe somebody, some other processes are using it. All right? Okay, if inside the memory map, if it says that this particular page is shared, okay, if it's shared, and, so if it's shared, then what happens is that for both the parent and the child, this particular page is going to be rewrite. Okay, so this picture sort of tells us that when you create the child process, you can't just go to the page table and then, I guess before I said that what you do is you copy the entire page table, okay, and then you set all the access bit to be read-only. Well, it turns out you have to do this a little careful because for the pages that are shared, you shouldn't set them to read-only. Okay, pages that are shared, right? This page is shared by both user processes. So if this guy wants to set it to 17, should it be able to do that? Sure, and it should do this without the interference of the operating system, right? If this guy wants to set this guy equal to 5, it will change this guy equal to 5. Okay? And then none of these operations will trap into the operating system because the page, you're not generating a page fault. All right, so sharing is very straightforward. And again, over here, whether things are shared or not, shared or private, that information is kept in the data structure, and this is kept in the memory map. All right, or the address space representation, whatever you call it. All right, what about if you have copy on write actually happen before the fork? Okay, so over here we have a parent process points to XYZ, okay, and then, how did the parent process get created? Well, it has its own parent, right, and that process has its own parent, etc. So eventually they all come from somewhere, right? So when the parent process, when it gets created, we follow the same rule, okay? All the private pages are read-only. Okay, so therefore, all these pages that it potentially can write to that are shared with its parent, they all are read-only. Okay, so this one, so you're going to set the private mapping, and you're going to get ready for copy and write. Okay, so now if this process tried to write to it for the first time, data equals 17, the same thing happened, right? And then you write into 17, and this guy is still 0. Okay, so what happened if you fork now? Okay, you modify the page already, and now you try to fork the parent process. All right, should the child process, where should the child process point to, right? The child process get a copy of the page table, so, the child process also point over here. All right, but in this case, it's rewrite, so this one will set it to rewrite. Then the child process will be able to write to this page. Okay, so then that doesn't really work very well. Okay, so therefore, should the child process point to the original one? Well, no, right? Because, you fork the child at the instance when the parent process has data equal to 17. Right? The idea of forking to a child process is that you get a copy of the entire address space, including all the values, all the variables that are inside the parent. Okay, so therefore the child's supposed to get data equal to 7 at the time of the fork. Okay, if you point the child to this page, then it's wrong, because the child shouldn't see data as original data that are sitting on disk. Okay, the child has to see data equal to 7, equal to 17, because it was forked after the copy on write. Okay, so now the child, this page, whether, no matter which way it points to, it doesn't really work. Okay, in either case, it's going to have a problem. So, all right, so over here, I guess, so the solution, right, is that what you have to do is that you make a copy of the page table, okay, and then again, you go down to the address space, okay, and look at, every page to see whether it's private or not. Okay, if it's private, you set it to read only again. All right, so the correct behavior is that this guy needs to point to the page that has data equal to 17. So of course it shouldn't point to this one, that's obvious. Okay, it needs to point to this one, but there's one more thing that you have to do. You can't just copy the page table. You need to turn every private pages back to read only so that you can do, so that you get ready to do copy on write again. Okay, but what about this guy? Okay, should this entry be set to rewrite? Right, if this guy is set to rewrite, this guy is going to modify it. It's going to say data equal to 5. And now the child process is going to get a surprise and say, hey, I thought data is equal to 17. Right, so even though this guy is read-only, if this guy doesn't modify data, if it reads data again, it's going to get the wrong data. Okay, so therefore the parent also needs to be set back to read-only. All right, so after you do the fork, what needs to happen over here is that this guy needs to go and change the parent process, look at the address space representation, and then again turn every read-only page, turn every private page back to read-only. Okay, and then this guy will point to the right thing. All right, so that's one complication of copy on write working together with fork. There's another problem, okay? So later on, when you try to fork, so let's say this guy, does a copy, okay? So to get a new copy, just point it to over here. And then, the child might have to fork again, okay? Or the parent might have to fork again, okay? Things starting to get very, very complicated. It gets to a point where you don't really know exactly where you're supposed to copy from. Okay, when you try to perform copy on write, you say, well, where do I copy from? Okay, so to manage all this complication, what's being introduced is something called the shadow object. Okay, so the shadow object is a one level of indirection, again, indirection to the rescue, because you don't really want to follow that pointer, because that pointer might point you to the wrong place. Okay, you got to copy on write, you got to copy the correct page. Okay, all right, so the shadow object is a kernel data structure. Okay, it holds pages that were originally copy on write, but it has been modified. Okay, so here's the shadow object. Okay, if this particular process, okay, if all you have are the original data pages, okay, then your shadow object is empty. Okay, every time when you perform a copy on write, then you need to remember that, hey, I have made a copy in this user process. Okay, so therefore you're going to make a reference in here to say that what have you made a copy of. Okay, so you're going to remember that object inside your shadow object. All right, so over here it says, a page in memory map into which an object was mapped private must have an associated shadow object. Okay, so as long as, so this sort of tells you what this picture means. Over here is the address space representation, or the memory map. And the memory map, there's a bunch of these these memory map objects, and in each one of these objects, I guess over here, this is called a VM area, okay? Or what we used to reference as a segment, right? Because we don't really want to represent pages in the kernel data structure that represent a user's address space, okay? Because then this list will be too long, okay? So therefore, we're gonna represent segments, and inside the segment, we talk about what information need to go into this memory object, right? So in this VM area, right? One is the beginning address of the virtual, the beginning virtual address that corresponds to the segment, how long the segment is, the protection for this segment, is it read-only, is it read-write, and then finally, whether the segment is private or shared. Okay, so that information is kept right here. Okay, so if this one is equal to private, then this VM area is going to point to a shadow object. Okay, if this VM area is not private, it's shared, then this one will point directly into things like file object and whatever. Okay, so the picture that we saw before, right, is that in the address space it directly points to the file object. Now it turns out that that picture is a little too simplified. Okay, if the page is if that segment is private, then it doesn't point to the file object. You have to go to the one level in direction and point to a shadow object, and the shadow object actually points to the file object. All right, so this way, when you get a when you get a page file and you decide, oh, I need to perform copy on write because this one says it's private, and then the page is read only. So therefore, when I try to do copy on write, I need to go through the shadow object in order to find out which page I need to copy from. All right, so we're going to sort of draw this picture of having pages inside a shadow object. Whenever you have performed the copy on write, so let's say that you perform copy on write on X, okay? So X over here basically points to a sort of a physical page. This is the actual page X. Over here, we just have a reference to page X, right? And remember, copy on write is that you make a copy of X, right? So this is X version 2 or something like that, right? You make a copy of this. You start a memory. You restart the write operation. So this data is going to be is going to have changed. So this thing is not going to be equal to this thing anymore. Okay, when you make this copy, you're going to remember that X2 is right here. Version 2 of X is right here. Okay, because later on, what you do is that when you need to do another, when you try to fork this particular user process, you got to decide, hey, where do I copy from? Okay, in that case, you need to copy this version of X and not this version of X. Right? Remember, right? If you do the copy on write before the fork, when you do the fork, you need to copy the most recent page that's used by that user process, okay, not some old pages. Okay, so the way that you do that is that you go to the shadow object, says, oh, who has the most recent data? Is it X or Y or Z? Now it turns out that X, you need to go to version 2, Y and Z, they're still in version 1. All right, so use the shadow object to remember, where these things are, right? So now X, this one refer to this particular memory page. All right. So if the page is shown to be inside the shadow object, okay, that means that this page has been modified. Okay. Otherwise, the page is associated with the original object. Okay, and the original object could be the file or even some kind of an anonymous object. Right. An anonymous object could be a page full of zeros, or it could be a page that we saw before that's already inside memory, and you inherit from your grandparents. Okay, but that one is modified by the grandparents to be different from the great-great-grandparents. But now you have the original copy from the grandparent. Okay, so this one again can be pointing to one of those pages. Okay, so these guys don't necessarily point to file; they can point to this other memory objects as well. All right, and the shadow objects tells you where to copy from when you need to perform copy on write. Okay, when you trap into the operating system and we need to perform a copy on write, you use the shadow object to tell you which page do you copy from. Do you copy from version number 1 or do you copy from version number 2? All right, so clearly, in this picture, you look for stuff in the shadow object. If you find it, well, then you should use the most recent version over there. Okay, if otherwise, you keep going down to find it in the lower level object. All right, we're going to see an example. Hopefully, this will make this a little more clear. If you have objects that are shared, right, so over here, this is the VM area, okay, and this one is shared. Okay, if it's shared, then it's like the previous picture. It points directly to things like file object. There's no shadow object. Okay, in this case, if you want to fork this user process, okay, what's happened is that you're going to create the second process, and again, over here, you copy the address space. If this is shared, this is also shared, so therefore they both will point to whatever the file object was before. Okay, so there's no shadow object getting involved. All right, so this is a simple case. Okay, so now let's look at private mapping. Right, so over here again the VM area. I'm going to just write VMA, okay, inside over here. This one is shared, sorry, is private. Okay, so if it's private, that means that there is going to be an associated shadow object. Okay, and the shadow object is going to point to, you know, the file object. All right, so over here again, this picture tells you that, you know, in the file object over here, it kept track that I have pages X, Y, and Z, and this one referred to this picture, where in the page table, page X, Y, and Z point to this. This is the actual page X, Y, and Z. All right, and these entries are set to read only. All right, I'm gonna sort of stop drawing this picture because pretty soon this page is going to be filled with other stuff. Okay, so remember the X, Y, Z basically represent, you know, the pages over here. Okay, and when you get copy, you can get, you know, Z prime, you know, and things like that. Then we're going to use, you know, other notations for that. All right, so this one I'm going to, you know, stop drawing them. All right. Okay, so if A modify page X, okay, and maybe this is, I should go back there one more time.
The time is 15 o'clock.
Okay, if A modify page X, right, what happened is that, you know, go back to the page table picture, it's read-only, you're going to trap into the operating system. The operating system is going to make a copy of, did I go back there? Okay. All right, so if you trap into the operating system, you got to get a new page, right, over here. This is going to be the new X, okay, and then this entry is going to be point to here and not point to there. And you restart an operation, you modify this. Okay, so in that case, what you will do is that you will make an X reference over here in the shadow object, and this one is going to be referring to this version of X. Okay, while inside the original file object over here, this X refer to the original X over here. All right, and the reason sort of this one points to this X is that, you know, you can see that there could still be another, you know, child process that's sharing that particular page. Okay, so in reality, things can get very, very complicated. All right, let's not pay attention to that right now. Okay, the shadow object and the mapping file object have, you know, backing stores. So this one, you know, over here, this is a note to say that eventually, if you need to swap out this particular, if you need to swap out this process, okay, when you swap something out to disk, well, later on you need to bring it back. When you need to bring it back, everything needs to be exactly the way you left it. So therefore, when you swap this process out to disk, everything over here needs to be swapped out to disk. Okay? So this guy also needs a backing store. All right? Okay. So now we have page X being modified. Right? All right. So now what you need to do is that you need to fork, you know, process A into process B. Okay. So what should that look like? Okay, so the idea over here is that when you fork off a process B, okay, every time when you fork and when you walk down the address space, look at all the VM area, if anything that's private, you need to create a new shadow object. Okay, because at that point, what you will do is that you will go and turn all the old, you know, private pages, turn all those pages to read-only. Right, remember that the example that we use, right, whenever you create a child process, you know, maybe some of the page has already been modified, so therefore all those entries you need to change them from read-write back to read-only. Okay, so we're going to use this hierarchy of shadow objects to keep track of, you know, when does an object go from read-write? Not when. At what stage of execution does a particular page goes from read-write back to read-only, because we got to get ready for copy on write again. All right? Okay, so therefore, in that case, when you fork over process B, the picture is going to look like this. You're going to get two empty, you know, shadow objects, and you're going to turn all the private pages back to read-only. Okay, so as far as these two processes are concerned, at this moment in time, there's going to be nothing, there are going to be no pages that has been modified. Okay, so remember, if a page has been modified, that is in the shadow object. So if you go to this process, says, has any page been modified? You go to the first shadow object, the first shadow object is empty. So therefore, as far as this process is concerned, no page has been modified. Okay, similarly, if you go to process B, and you say, has any page been modified? It comes to the shadow object is empty, so no page has been modified. Okay, so again, if you go to any VM area, as long as it's private, then, when you do the fork, at the instance of the fork, all the shadow objects will be empty. All right, and the way to do this is to create 2 new ones, and they will point to the previous shadow object in this case, because, going through the shadow object is still how you find out which data to copy from. All right, so now this is going to be the picture. Okay, the next thing you do is that A will modify page Z and B will modify page Y. Okay, so A modify page Z, right? X, Y, Z, they're all copy on write, right? So if you try to write to it, you're gonna trap into the kernel. Kernel is gonna allocate a new Z here. So this is Z version number 2. Okay, so this guy will point to Z version number 1, right? So this is version number 1, and this is Z version number 2. It's going to copy the entire content from Z version number 1 into Z version number 2, and change the page table so that this entry is going to be rewrite. So from this point on, you can rewrite into this page. Okay, and also one more thing you have to do now is to remember that this guy will have Z version 2. Okay, because remember, shadow object keeps track of all the all the pages that were originally copied on write and have been modified. Okay, so therefore this guy will say Z version 2. All right, so from this point on, if process A starting to modify page Z, you won't cause any page fault, right? It will just keep writing to this page. All right, which is sort of the right thing, right? Because you don't want process B to see any of this changes. Similarly, process B will modify page Y, right? This guy used to point to this page Y over here, and this is Y version number 1. The kernel is going to allocate Y version number 2, make a copy of everything over there, okay? And then change the page table so that's become rewrite. And also remember Y version number 2, remember that in the shadow object. Okay? So now, any future copy on write will be done through this object. Okay, so again, process B will change things over here, and that's okay, because it's not going to affect process A, right? Because process A is working on a copy, process B is only working on a copy, and if somebody else is looking at the original Z and Y, well, it's still going to be okay. All right, because there could be more user processes that are sharing many, many things. Okay, so therefore now the picture sort of look like this. Okay, inside here, they remember Z version number 2, and over here, remember Y version number 2, and over here, remember X version number 2. All right, let's continue. Oh, over here, well, it says that, when you try to perform copy on write, okay, where do you copy from? Okay, how do I know that, this particular Z, I need to copy, start with this one, make a copy? Okay, so there's a rule that you have to follow. To find a page to copy from, so when you trap inside the kernel, you look at, so how do I get here? Oh, well, a VM area is private, and the user process is doing a write. Well, that's copy on write. Okay, so therefore, when I need to figure out where to copy from, the rule is that I need to go down this chain. Why do I say a chain? Doesn't this look like a tree? Why, as far as the user process, so this is the upside down tree, right? Okay, where the root is at the bottom, and then, you have something starting from the top to point to it. So from any user process, it's a linked list. Okay, even though the whole thing looks like upside down tree. Okay, so over here, you start at the top of the linked list, and you follow this, singly linked list. Okay, try to look for the right page. Okay, so when A is modifying page Z and get the page file, inside the kernel, you start looking for Z, say, why is Z in here? Originally, it's not in there. It's not in here, and Z is right here, and that's the page you copy from. Okay, so the rule is that you start with the process memory map and follow the chain of shadow objects. Okay, if you find something, that's where you copy from. If you don't find it, then well, eventually you have to find it. Otherwise it's a segmentation fault. All right. If turns out that A wants to modify X, then it will find X in here, and it will copy version number 2X into version number 3X, and not copy from version number 1X. Right? And the reason that this is the correct X, because this X has been modified before the fork of the process B, so therefore you need to copy from the right one. Okay, so using this very simple algorithm, you can find the right version of the memory page to copy from. How about B, try to fork, creating process C. What should it look like, right? Again, you create process C. Everyone gets its own shadow object. They all point to this guy, okay? So therefore, the resulting picture is going to look like this, okay? So again, at this point, okay, at this point, right? This, this shadow object is empty because as far as process B and C is concerned, every copy on write, object has not been written into. Okay, so therefore, when you fork process C, you got to go to your page table, and then for every for every private page, you need to change from read write to read only. Okay, so none of these pages have been modified. That's why the shadow object is empty. Okay, so at this point, if you want to perform copy on write from this point on, B will find Y right here. B will find X right here, B will find Z right here, and same thing with C. C will find right here, Y right here, C will find X right here, and C will find Z right here. Okay, so now if B try to modify page X, okay, we're going to follow that rule, right? You're going to trap into the kernel is going to start walk down this chain of shadow object to determine where to copy from. It will find X first right here, right? It's not here, it's not here, it's here. Okay, and this is X version 2, right? So therefore, this guy point to this guy, X version 2. It will make a copy of that, X version 3, okay, and put X3 right here, point to it, okay, change it to rewrite, and then restart that memory operation. Okay, Z, want to modify page Z, okay, you trap into the kernel, this guy won't find Z over here, will not find Z over here, won't find Z over here, find Z version 1 over here, right? This guy point to this one, Z version 1. Make a copy of it, Z version 2, copy the entire content, have this guy reference Z version 2 right here, okay, and then, change the memory map to be rewrite, and then, allow, and then return back to the user process. All right, so this goes on forever, right? C forks D, A forks F, so this picture can get really, really messy. Okay, and I think in the kernel 3, one of the tests is called mem tests. Okay, it's actually trying to create this whole mess to make sure that you implement this perfectly. All right, so this can create trouble. All right. Okay, in Unix, the last guy at the bottom, has a creative name called the bottom object. Okay, so this doesn't really have to be associated with a file. It could be associated with memory or devices. Okay. So when it's memory, that means that it points to, it will be pointing to an anonymous object, okay, a page of 0, or maybe some other thing that you copy from in the previous case. And all these object type, right? So how do you make a linked list of mixed object types, right? This is the linked list. Here's a shadow object. Here's a shadow object. This one could be a file object, could be an anonymous object. So therefore you have to use polymorphism. Okay, so that's why I sort of want you to walk through the code of kernel 2 polymorphism. When you go through from the virtual file system to actual file system, you will actually switch to use polymorphism so that you can execute any code inside the actual file system. In kernel 3, we're going to switch from the actual file system being the RAM file system to the system file system. So in that case, that's a very simple switch. You switch, instead of you have an instance of the RAM file system, plug it into your virtual file system. Now you have an instance of the actual file system, plug into your virtual file system. Okay, so that's fairly straightforward. Whatever function that you call, you just call, one of the actual file system functions. Okay, but now the polymorphism over here becomes a little tricky because now you have 3 possible things. Okay, so from the higher level, you have to deal with 3 different object types. Okay, and only one of them will be plugged in. Okay, what makes it even worse is that now, you have a linked list of things, and you need to sort of find something, in these pages. Well, you can write, when you find something, you can use a loop, or you can use recursion. Okay, there are some code that should be done using recursion. So what you need to worry about is that if you have recursion, one of the biggest problems is that if you don't do it carefully, you're going to end up with an infinite loop. Okay, so therefore, I'm going to ask you that when you see some of the code that you have to implement for all these memory objects, think about it a little bit and say, how do I stop recursion? Okay, so what happens is that there are different functions. One is called looking up the page. The other one is called fill out a page. When should you look something up? When should you fill something up? When should you, whose function should you call to fill out the page? Okay, do you call, the function at the higher level or the superclass, and you can C++ terminology, call the function in the superclass or call the function in the subclass? Okay, so remember that if you have to write recursive code, usually the recursive code template is that, here's something, a function recursive R, right? You have to take care of the base case. Okay, the base case is what stops the recursion. Okay, so the first thing you have to do is to identify the base case so you can make sure your recursion is stopped. And if it turns out if it's not the base case, then you recursively call R. Okay, when you recursively call R, you have to make sure that you go to a smaller problem, okay, so that recursion will stop. Okay, if you call recursion and you end up to be a bigger problem, then you're going to get bigger and bigger and bigger and you never stop. Okay, so think about this when you write these recursive functions. Identify the base case to think about what's a reasonable way to stop the recursion. Okay, then you will end up doing the right thing. Okay, don't just start writing a bunch of code and try to debug it. Then it's probably not going to work very well. All right? Okay, and please read the kernel 3, FAQ, because there might be hints of, what you're supposed to do. All right, there's a bunch of stuff that get X'd out. All right, so shadow object summary. Why go through all this trouble, right? Because we want to implement copy on write together with fork. Okay, so a variable such as the data in a few slides back. Okay, that variable could be a global variable, could be a variable in the stack, could be a variable in the heap. Okay, they can exist in many different physical pages simultaneously. Okay, every one of these a variable. Okay, there are different, incarnation of them that are inside different physical pages. Hello, please don't talk. I mean, make a lot of noise. All right. All right. Every one of this contains a different version of this variable. Okay, so we use the shadow object to make sure that you copy from the right one. Okay, so that the parent process, the child process, no one actually get a surprise behavior. Okay. To manage this mess, Unix also used the idea of shadow object. Okay, and what is the idea, right? Is to organize a tree, this inverted tree of shadow object, using this inverted tree data structure. Okay, where the root is the bottom object, the root is at the bottom, that's the bottom object. Okay, and we're going to use this rule, so when you try to find stuff, you have to use the rule. Okay, use the rule of finding physical page frame that contain this global variable, that you're looking for in a particular manner. Okay, so that you can find out which process it belongs to, and first you need to go to which process it belongs to, find the right VM area, and then go down that list, try to find out, where do you copy from. Okay, traverse shadow object, point to the inverted tree, and eventually when you reach the bottom object, if it's not in the bottom object, then it's a real segmentation fault. Okay, otherwise, the kernel is there to fix it. Okay, and when and where to perform copy on write. And then at what point do you set the page table, modify the page table to switch from read-only to read-write, and sometimes you have to switch it back when you do a fork from read-write back to read-only. In Unix, to manage page frame, they use, this thing called object, the memory map object. Okay, so the VM area actually points to memory map objects. And the memory object, there are 3 kinds, and that's where polymorphism kicks in. Okay, so the important types of memory object, there are basically 3 that you're going to deal with. One is the one that's already inside the file object. Okay, so inside the vnode, you probably never noticed this. There's something called, you probably never use it. It's called vnode object. Okay, so that's the one that's used to manage page frames for the vnode. So if the vnode wants memory, okay, because like the file is increasing in size, so you need more pages to hold the data for this file. Who do you go to get more physical memory? Well, you call upon the services of the memory map object to get more memory. Okay, so that's one. It's inside the vnode. The shadow object using polymorphism is implemented as a memory map object. And also the anonymous object is managed, is also implemented as a memory map object. Okay, so these are the three types of memory map object that you have to deal with. Okay, and remember that when you have this inverted tree, everything in the middle, they're all shadow object. Okay, the bottom is either the first kind or the third kind. All right, and that's sort of how you stop the recursion. All right, when you reach the first kind or the third kind. The VM area is supported by one of these three memory objects, right? If the VM area is shared, then they point directly to the file object. If it's private, then there's going to be a chain of memory object that's over there. Okay, this one is private. There's going to be a chain of shadow objects there, and eventually point to a VM, point to a bottom object. In this case, the bottom object, if this is not a memory map file, or if it's like heap or something like that, then you know that in the end, it's going to be an anonymous object, right? Okay, if things are not, the first kind, then, at the bottom, it has to be the third kind. All right? Same thing with the stack, right? The stack, they don't map to file, right? So eventually, if there's a chain of shadow object, then at the end, the bottom object has to be an anonymous object. All right? All right. I guess there's the last part talking about backing store. I guess I sort of briefly mentioned it. I talked about backing store, quite a few times already, right? So for things that map to files, you need a backing store. For example, a text area. For things that are memory mapped, they need a backing store. Okay, so those things are sort of obvious. If you manage them with the file object, and inside, in Unix, using the memory map object inside a file object, you can, read pages from the disk or write pages out to the disk using the operation of the memory map object. Okay. There are other things, that also require backing store. Okay, so the first, I guess the previous page, all those things you sort of know where to go, in case you need to read data back from the disk, right? That's where the data come from originally, in the executable file. Okay, all the other ones, the other memory objects that you use, well, then those guys you need to allocate backing stores for them. Okay, and these include the private mapping of the file, as well as memory, as well as things that are being used in a memory map system call. Okay, and this include the shadow objects, all the other all the memory objects that are being used. They need to have a backing store. All these kernel data structure, when you need to swap out the entire process, they need to have a place to go to on the disk. You need to allocate them. Okay, and all these anonymous objects. Okay, they started out with a page full of zeros, or they could be the data segment of a parent process. Once you perform copy and write on it, then they become memory objects. Okay, so those guys also need their backing store. Okay, so that's also how you sort of write your shadow object onto the disk. In that case. All right, 1 minute. So as it turns out that you don't have to worry about this in Unix. Because Unix, again, it's a simple operating system. It doesn't implement a backing store. So what do you, how do you make sure that, some of these, when you run out of memory, you know that there's a page-out daemon, right? So the page-out daemon will try to write things onto disk. Okay, so how do you make sure that they don't go onto the disk, right? What you do is that you remove them from the list that the page-out daemon look for, move them onto a different list. Okay, so when you move them to a different list, then the page-out daemon will not see these pages. So therefore, even though, so they're not eligible to go to disk. Okay, so therefore, page-out daemon is not going to accidentally write them to disk. Okay, so the idea is basically you pin them to a different list, and then the page-out daemon won't have any access. All right, I'm out of time. I guess there's only 6 pages left in Chapter 7, so next time I'll start finishing them. We're going to go back to Chapter 6 and talk about crash resiliencies.
That concludes this session of Computer Science 402 with Professor Cheng on Wednesday, July 16th, 2014. From your studio operator, Rex, have a wonderful evening and a great rest of the week.